Hello, my name is Sang Yanni, CEO of BeSang Inc. Today, I would like to discuss about three-dimensional integrated circuit, opportunities, challenges, and BeSang's proprietary True 3D IC. According to 2013 ITRS International Technology Roadmap for Semiconductor, scaling of logic transistor was expected to go down to 5 nanometer until 2028. However, in 2015, ITRS modified the roadmap and predicted logic transistor scaling limitation at 10 nanometer. In case of memory devices, DRAM and NAND faced scaling limitation at 18 nanometer and 14 nanometer respectively. However, we don't fear these scaling limitations because many products are still using older generation technologies and gradually moving to advanced technology nodes using tool upgrade. So many devices are still achieving 25 to 35 bit growth every year. However, such bit growth will end in few years. Then what will happen? I don't know. The semiconductor industry should find out and accept innovation. Otherwise, lifespan of CMOS integrated circuit will end soon. Okay, let's check cost reduction of logic process technology. For your information, logic process is being used for application processor for smartphone, CPU for your personal computer, GPU for gaming, DSP, FPGA, ASIC, system on a chip, and etc. As shown in this graph, device shrinking does not create cost advantage anymore. Then, where is innovation in the semiconductor industry? I think the semiconductor industry has too much confidence in lateral scaling. Since the beginning of integrated circuit, engineers have always found solutions for device scaling, even though there were so many warnings regarding scaling limitation. However, most people in the semiconductor industry admit that end of scaling limitation in 2016. Even though device scales could go down a little bit further, it is difficult to expect lower cost anymore. Unfortunately, semiconductor industry has focused on lateral scaling for a long time and has never been changed since its beginning. Recently, NAND makes transition from planar to vertical scaling. So, does NAND find out an ultimate solution? Answer is no. No cost advantage is observed from 3D NAND yet. Here is the comparison of $ per gigabyte of SSD at Amazon.com. Planar NAND is still much cheaper than 3D NAND. We expect more memory cell stacking layer of 3D NAND would be cheaper. However, ironically, 48 layer is more expensive than 32 layer 3D NAND. Recently, Toshiba SanDisk introduced 64 layer 3D NAND. People expect that 64 layer could achieve price parity with planar NAND. However, no cost per bit information is available in public yet. If we compare Samsung and Intel Micron 32-layer 3D NAND is more expensive than Samsung 32-layer 3D NAND. For the time being, Samsung takes good profit at the high-end SSD market with 3D NAND because 3D NAND has better functionality and reliability compared to planar NAND. However, such advantage will be disappeared as other 3D NANDs come to market. In addition, 3D NAND needs 3 to 5 times more fab investment compared to planar NAND. It means problem with the semiconductor industry get worse. So 3D NAND is still in maze and no one knows when 3D NAND will be cheaper than planar NAND. Regarding 3D NAND, details are discussed at the following video tutorial. Please check the video for more information about 3D NAND. Let me explain semiconductor domains first. At the transistor level, FinFET is being used because it is difficult to scale planar transistor considering leakage current. 3D IC implements transistor on top of other transistors regardless type of transistor. If we compare 3D transistor and 3D IC, they are totally independent. 3D IC could utilize planar or 3D transistor. 3D IC is also independent to device feature size. If you ask the feature size of 3D IC, in fact, you just ask the feature size of transistor inside of 3D IC. So don't get confused. 3D package stacks multiple ICs to vertical direction. 3D package is also independent to the type of transistor and IC. Some people in 3D package domain are using the name of 3D IC. That is not correct. Here is comparison between 3D IC and 3D package. Even though 3D package provides high bandwidth with hundreds interconnects between chips compared to other package technologies, it cannot be compared with the 3D IC, which has millions of interconnections in given area. Also, 3D package is not low-cost solution. Here is cross-sectional view of a logic integrated circuit. There are at least 15 to 20 different transistors on top of silicon surface. Each of these transistors have different gate oxide, channel doping, and weld formation through multiple high-temperature heat cycles. Optimization of single transistor is not difficult at all. However, optimization of 20 different transistors at the same heat cycles is extremely difficult. On top of transistors, there are multiple metal interconnect layers, which are very important to carry electric signals. Processing temperature for back end of the line is strictly limited to 400 degrees Celsius. Where 3D IC works, technically it is impossible to implement logic IC on top of logic IC. In 1980s, many Japanese companies, research institutes, and universities had extensive works on 3D ICs. Unfortunately, they were all failed. Since then, many works on 3D IC have been done. However, all these works did or are doing the same mistakes. Technically, it is not possible to optimize various transistors at below 400 degrees Celsius. Multiple ion implantation, annealing for damage cure, dopant activation, thermal diffusion, junction depth optimization, leakage current, and breakdown voltage optimizations are extremely difficult things to do. If you have 3 to 5 years hands-on experience on FEOL process integration, you may understand what I'm talking about. Economically, there is no reason to implement 3D IC at all. Considering yield and manufacturing cost, simple large size 2D IC should be much better than 3D IC. Folding 2D IC to implement 3D IC does not provide cost reduction at all. We should think if there is a way to reduce manufacturing cost of 3D IC. Logic IC on top of logic IC is unable to be a solution for scaling limitation. We should ask these questions in advance for the consideration of 3D IC. Will it be cheaper than 2D IC? How about yield? As shown in this picture, yield of 3D IC could be a significant problem. Will low temperature work? Is it technically feasible? As mentioned, it is technically impossible to optimize 20 different transistors at below 400 degrees Celsius. Will it make manufacturing simple? Will it reduce fab investment? Answer should be no, right? Is 3D IC able to defy scaling limitation? I mentioned that 3D IC is not related to transistor scaling. However, if 3D IC enables further scaling of transistor, it should be an ultimate solution. BeSang's true 3D IC has answers for all these questions. Okay, let me introduce BeSang's True 3D IC. It implements memory cell on top of logic IC. Unlike logic IC, which needs 15 to 20 different transistors, the memory cell needs only one transistor type. So it is possible to optimize the single transistor at below 400 degrees Celsius. True 3D IC does not increase mask steps. In fact, it reduces total mask steps. You may wonder how memory on top of logic could defy scaling limitation and provide significant cost and performance benefits. As shown below, it enables die size reduction. So die per wafer increases and die cost decreases. In addition, power consumption of a memory subsystem decreases 75%. Speed increases 10 times compared to off-chip memory, and cell density increases 100 times when we compare embedded SRAM and BeSang's embedded DRAM. Let me explain more details at the following slide. Memory is the number one functional blocks in most high-performance logic products. More embedded memory is better for high performance because embedded memory is about 10 times faster than off-chip memory. However, embedded memory is about 100 times more expensive than off-chip memory considering cell density difference between embedded SRAM and off-chip DRAM, and product price difference between CPU and off-chip DRAM. Embedded memory could reduce power consumption up to 75% in the memory subsystem because no I/O is needed between CPU and off-chip memory. Embedded flash memory will be a crucial portion of Internet of Things for large data storage, fast data access, low power consumption, security update, and small form factor. You may argue that not all logic products are using embedded memories. Yes, that is true. Though, True 3D IC could combine off-chip memory with logic products. Therefore, it could significantly reduce total cost and enhance the system performance at the same time because most high-performance logic products heavily depend on off-chip memories. Let me answer the question on True 3D IC. Will it be cheaper than 2D IC? More die per wafer with less mask steps enable low cost. How about yield? Less mask steps and small die size increase yield. Will low temperature work? Yes, it works fine. Is it technically feasible? Yes, prototype works well with the high yield. Will it make manufacturing simple? Yes, in case of embedded NOR, True 3D IC saves 5 to 7 extra masks. Will it reduce fab investment? Simple mask steps will enable low fab investment. Is it good for low power? As mentioned, up to 75% reduction of power consumption is expected. High performance? Yes, it is 10 times faster than off-chip memory. Is 3D IC able to defy scaling limitation? Yes, it enables 100 times cell density compared to embedded SRAM. Let me explain this on the next slide. The graph shows Intel's embedded SRAM cell size. X-axis shows technology feature size, and 2 Y-axis shows cell size with different units. One with micrometer square and the other one with F square, where F means technology feature size. SRAM used to be 100 F square at 100 nanometer feature size. It now becomes more than 300 F square at 14 nanometer feature size. It means SRAM becomes inefficient. At 22 nanometer node, BeSang's True IC could install 100 times more embedded DRAM cells compared to SRAM. This is a yield map of 3D interconnects. It is important because wafer was processed successfully at below 400 degrees Celsius at a conventional CMOS FET. Memory shows excellent characteristics and reliability. It is clear that lateral device scaling faces its limitation, so vertical scaling is the only option for the semiconductor industry. For a long time, semiconductor industry is searching for the solution for vertical scaling. Unfortunately, all failed. 3D NAND successfully started mass production. However, we don't see cost advantage from 3D NAND, and now it is going to wrong direction. In case of logic, it is not possible to implement logic IC on top of logic IC at low temperature. In addition, there will be no cost reduction even if that works well. BeSang successfully generated true 3D IC which implement high-density memory cells on top of logic circuitry at low cost. It will create huge value for logic products. 75% reduction of power consumption from memory subsystem, 10 times faster access time compared to off-chip memory, and 100 times more cell density compared to conventional embedded SRAM. Please feel free to contact BeSang and ask how BeSang could significantly leverage your next products. Thank you for watching. Have a wonderful day.